All right. 12 points are spaced evenly around a circle, lettered from A to L. Let n be the total number of isosceles triangles, including equilateral triangles, that can be constructed from 3 of these points. A different orientation of the same lengths counts as a different triangle because a different combination of points form the vertices. What is the value of n? All right, this is a pretty wordy problem, but let's boil it down to its basics. This is asking us how many isosceles triangles can I draw with 3 of these 12 points? So I could sit here and count up every single possible isosceles triangle, but I don't have the time or the doodling ability to do that. So instead, since all of these points are evenly spaced, why don't I just take one case and extrapolate it to the others? Maybe let's start with A. Why not, right? How many isosceles triangles can I draw from A? Well, I could start with ABL. That's an isosceles triangle. How do I know, by the way? Well, the points are evenly spaced, right? So this distance has to be equal to that distance, since A is evenly spaced from L and A is evenly spaced from B. How many other isosceles triangles can I draw from A? Well, I could do ABL right there. I could do ACK. I could do ADJ. I could do AEI. And I could do AFH. And so that is how many? 1, 2, 3, 4, 5 isosceles triangles I was able to get from A. And the problem told me that a different orientation of the same lengths counts as a different triangle. So I'm not done counting. I need to do this for every single point. Well, how many points do I have? I have 12. So it's 12 times 5 should give me 60. And unfortunately, that's not the correct answer. But if you got that far, then give yourself a pat on the back. Because there's one last item that we need to consider. Now, it's true that different orientation of the same lengths count as a different triangle. But it's not saying that we can count the same triangle multiple times. Well, did we do that? Yes, we did. And here's where we did it. So let's zoom in on one of these particular isosceles triangles we drew. AEI is an isosceles triangle, but it's also an equilateral triangle, right? The distance from A to E, again, evenly spaced, 1, 2, 3, 4 points, is the same as the distance from E to I, evenly spaced, 4 points, 1, 2, 3, 4, is the same as the distance from I to A, another 4 points, 1, 2, 3, 4. So that's an equilateral triangle. Again, this might seem confusing since they say, a different orientation of the same length counts as a different triangle. They are not saying that you can count the same triangle multiple times. The triangle AEI is the same triangle as the triangle EIA. So let's start subtracting from our total. We calculated that there were a total of 60 isosceles triangles, but we overcounted, right? We counted some of these equilateral triangles multiple times. So before we go any further, let's just point out, right, it has to be fewer than 60 since we're going to be subtracting from here. So it can't be 60, it can't be 72, and it can't be 120. That means that it has to be A or B. So we're down to a 50-50. All right, now let's get to answering this exact question. How many times did we overcount equilateral triangles? Well, when we did all of our triangle drawing from A, we counted this equilateral triangle here. And then we also counted it when we did that from E. And then we also counted it when we did it from I. So we should have counted this triangle only one time, but we counted it 3 times. In other words, we counted this triangle 2 extra times. So to be fair, we need to subtract 2. How many times overall did we do this? Well, we did it with the points BFJ. That's an equilateral triangle, so we need to subtract another 2 from this. And then we did it with the points CGK, so we need to subtract another 2. And then we did it again with the points DHL. There it is, another 2. So we don't have 60 triangles. In fact, we have 60 minus 2 minus 2 minus 2 minus 2, which comes out to 60 minus 8, so 52. And 52 is the correct answer here.